Once again, we're considering a sphere of radius big R. In previous examples, this represented the Earth with a density function 12 minus 9 rho over R. We previously integrated to find the mass and the moment of inertia, reconciled at least the mass and pretty much the moment of inertia with the accepted and expected values, and that seems to have worked out. Now, we could have described everything in in cylindrical coordinates, r, theta, z. The only difference being that instead of rho, we're going to use the square root of r squared plus z squared. So, because that is the relationship, of course, between rho and the polar coordinates r and z. Or we could represent this in rectangular coordinates, where rho is the square root of x squared plus y squared plus z squared. So these three density functions are all the same, simply expressed in terms of different coordinate systems. The sphere is easily described in terms of spherical coordinates by these inequalities, which we've just seen. In terms of cylindrical coordinates by these quantities or inequalities, which we've seen previously, and in terms of rectangular coordinates by these inequalities. Volume increments are rho squared sine phi, d rho, d phi, d theta in spherical coordinates, and we've seen in detail why that's the case. dv equals r, dr, d theta, dz in cylindrical coordinates. Not difficult to understand, especially in terms of the area increment for polar coordinates multiplied by the z increment. And in rectangular coordinates, where the expression is probably easiest to understand because the typical volume region is just a rectangle, delta x by delta y by delta z, giving us the dx, dy, dz volume increment. Now you can tell at a glance that I've tried to get too much onto this page. Wanted to represent all three of these quantities in a column, but that's not going to be possible. However, let's just again compare the volume increments. To get the volume, we simply integrate the volume increment over the region, so that these inequalities give us this order of integration, and it really doesn't matter in what order we integrate in this particular case, as long as there's really no restriction. So that if we want to let rho go from 0 to r, then theta from 0 to 2 pi, and phi from 0 to pi, that's fine. In other integrals, the order might make a difference, but since there is no rho, theta, or phi dependence in any of these limits, there's no reason for one particular order of integration to take preference over any other. Okay, in cylindrical coordinates, again, we set up our limits on the integral according to our inequalities, and we integrate the volume increment. And the same in rectangular coordinates. The inequalities we choose with which to describe the region and dictate the order of our integration. Now, unlike in spherical coordinates, the order of integration does make some difference in cylindrical coordinates. Since our z limits depend on r, we have to integrate z before we integrate r or theta. Now, we could then integrate with respect to theta or with respect to r. It wouldn't make any difference because neither of these limits involve either of the other functions. They're both constant limits. With this with this set of inequalities, our order of integration for rectangular coordinates is dictated by the fact that our z limits involve both x and y, so that we have to integrate z first. Our y limits involve x, so we have to integrate y before x. And x then will be the last variable with respect to which we perform the integration. Each coordinate system has its advantages for this volume integral. Okay, the volume increment is simplest in rectangular coordinates, but the limits on the integrals are more restrictive, whereas in volume spherical coordinates, our volume integral has a more complicated volume increment, but the limits on the individual integrals are much simpler. Now, I attempted to squeeze in the mass integrals, and that didn't work out very well, so we're going to go on another page and look at that. But in general, the mass is whatever we get when we integrate with respect to volume, when we integrate the density with respect to volume. Because density times volume increment gives us mass, when we sum this up, i.e. integrate it, we do get the total mass. Now this looks like a single integral where we know that a volume integral is going to be a triple integral, but we just use the integration sign here to indicate a summing up of all our density times volume increments, and you can see where I've actually written out the mass integrals for the spherical case and for the rectangular case. These are going to, for the cylindrical case. Started the rectangular, realized this was a mess, and so again we're going to stop here very shortly and then go on with these integrals and make the comparisons. One important point is the volume of this region, the volume of this sphere is what it is, and it doesn't matter whether we find it in spherical, cylindrical, or rectangular coordinates. We're going to get the same result if we do the integrals correctly in any of these systems.